In this lesson, we're going to talk about finding new Maclaurin series from known Maclaurin series. We're going to do composition, addition, and subtraction. This theme of finding new series from old series will continue for more videos than just this one. So first of all, here's a list of some common Maclaurin series. A lot of these are on the IB formula sheet. Not all of them, and I'll point that out. So the first is e to the x. It turns out that e to the x can be modeled by the sum as n goes from 0 to infinity of x to the n over n factorial. Or if you look at the first few terms, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. So that's what that series is. And it converges for all x in the set of real numbers. In fact, it actually converges for all complex numbers as well. Sine x is the sum as n goes from 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 quantity factorial. So it's an alternating series, positive, negative, that's what that thing does. And it also starts with a positive term because when n equals 0, negative 1 to the 0 is positive. Then it has odd numbered exponents divided by the corresponding coefficients. So x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, etc. Also converges for all real numbers, in fact, for all complex numbers. Cosine x is the sum as n goes from 0 to infinity of negative 1 to the n x to the 2n over quantity 2n factorial, again alternating, starting with a positive term. And then it has even exponent, x to the 2n, and then divided by the corresponding factorial. And here it is again, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to 6 over 6 factorial, etc. Also converges for all real numbers and, in fact, all complex numbers. Arctangent of x is the sum as n goes from 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1. Notice the denominator is not a factorial. It's just 2n plus 1. So alternating, start with the positive and then negative, and then x to the odd number divided by the corresponding odd number. So x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7. It will kind of look like sine, except that don't forget these are not factorial, so that's really critical. And also, it doesn't converge on all real numbers. It only converges as long as x is between negative 1 and 1 inclusive. Or in other words, absolute value of x is less than or equal to 1. The natural log of 1 plus x is the sum as n goes from 1 to infinity of negative 1 to the n plus 1 over times x to the n over n. Notice this one starts at n equals 1 and goes up. It doesn't start at n equals 0. Also, when n equals 1, you get negative 1 to the 1 plus 1, in other words, negative 1 squared. So this first term is going to be positive again, and then x to the n over n. Again, not a factorial in the denominator. So x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, etc. This is not odds and evens, it's just all the terms, except it doesn't have an n equals 0 term. So no constant in the front. And it converges for all x in between negative 1 and 1, not including the negative 1, but including the positive 1. And then this is our familiar binomial expansion for rational values of p, and I'm not going to write out a special example of that because p could be anything and every single p will have a different looking series, but this is the formula that is in the formula sheet, and also we did when we did the binomial expansion for rational exponents. We know, of course, it converges for all x between negative 1 and 1 exclusive, where absolute value of x is less than 1. Now this one over here is actually your geometric series, sigma as n goes from 0 to infinity of x to the n. That's the series. The first term is 1. The common ratio is x. So the sum of the infinite series is 1 over 1 minus x. So this is in reverse. 1 over 1 minus x has this Maclaurin series, 1 plus x squared plus x cubed plus da. And of course, it only converges for all x absolute value of x less than 1, or in other words, x between negative 1 and 1 exclusive. So this is again a list of some common Maclaurin series, and we're going to use those to develop new ones. So here we are asked to find the Maclaurin polynomial of fourth degree for 1 over 1 plus 3x, and then we're supposed to state the interval of convergence of the series. So of course, when I do a Maclaurin polynomial of fourth degree, I'm not going to have an infinite series, but the series itself will have a particular interval of convergence. So the first thing I notice is I don't actually have a formula for this from one of the basic Maclaurin series, but I do have something that looks sort of like that, and that is 1 over 1 minus x. And the series for 1 over 1 minus x is sigma, as k goes from 0 to infinity, of x to the k. That is the geometric series, and of course it converges for all absolute value of x less than 1. Now this doesn't quite look like that, but I can manipulate it a little bit to make it look more like this. I can call it 1 over 1 plus 3x is really 1 over 1 minus negative 3x. And so the reason I do that is because 1 over 1 minus something is essentially what this is, 1 over 1 minus something. And I have a formula for that. So I can substitute this negative 3x into this and therefore into this series. So I'm going to end up with sigma as k goes from 0 to infinity of negative 3x raised to the k, essentially plugging negative 3x in over here. Now, I don't like the way this is written because it doesn't look like coefficients and x to the somethings, so I want to separate that out a little bit. So there's actually 3 pieces I'm going to separate out here. First of all, sigma k goes from 0 to infinity. First, I've got that negative to the k, so I'm going to write negative 1 to the k. And then I'm going to have 3 to the k, so I'm going to write 3 to the k. And then finally, I'm going to have an x to the k, so x to the k. And the reason I like to write it this way is because the negative 1 to the k times 3 to the k, those become the coefficients, and then the x to the k is how we end up with the polynomial. Now, this is actually the Maclaurin series that I've just figured out. So let's go ahead and talk about the interval of convergence of the series before we do the Maclaurin polynomial of 4th degree. Now, the interval of convergence of the original series, the Maclaurin series that I worked with, is absolute value of x is less than 1. I substituted negative 3x in for x. So I'm going to substitute negative 3x into the interval of convergence statement. So the interval of convergence here will be absolute value of negative 3x less than 1. Well, this negative part doesn't really matter because I'm doing an absolute value, so I might as well call it absolute value of 3x less than 1. What I want is to talk about what x is doing, so I'm going to divide both sides by 3, and again, absolute value of 3 and 3 are the same thing, so that doesn't change anything. So really what I'm saying is absolute value of x is less than 1/3. And now I can change that into an inequality, or I can do it with bracket notation. Let's do it with bracket notation. X in the element of outward facing brackets negative 1/3, comma 1/3, another outward facing bracket. So this is now the interval of convergence of this new series that I discovered. And again, all I did was I took the interval convergence statement that I had for the original one that I already knew. I plugged in the substitution negative 3x into the interval of convergence statement and just worked out what that meant about x for that particular interval of convergence. Now I'm going to do the polynomial of 4th degree because that was, again, part of what I was told. So m sub 4 of x. Well, that just means I got to start plugging in k equals 0, 1, 2, 3, etc. until I get to k equals 4 into this series. So when k equals 0, I end up with negative 1 to the 0, which is 1, 3 to the 0, which is 1, x is 0, which is also 1. So this whole thing is just 1. Now when k equals 1, I get negative 1 to the 1, which is negative, 3 to the 1 is 3, and then x, so minus 3x. When k equals 2, I get a positive, 3 squared is 9, and then x squared. When k equals 3, I get negative 1 to the k, negative 1 cubed is negative, 3 cubed is 27, and then I get x cubed. And when k equals 4, negative 1 to the 4th is positive, 3 to the 4th is 81, x to the 4th. And that is now the 4th degree Maclaurin polynomial for this particular function. So let's find the Maclaurin series for sine of x squared. So once again, I'm going to start with the Maclaurin series for sine of x, which is, sine is an odd function, so I'm going to use k again. K equals 0 to infinity. Sigma k goes from 0 to infinity, negative 1 to the k, x to the 2k plus 1 to get the odd numbered exponents over 2k plus 1 factorial, and I want sine of x squared, so I'm going to substitute x squared in here. So I'm going to get sine of x squared equals sigma as k goes from 0 to infinity of negative 1 to the k, x squared to the 2k plus 1 over 2k plus 1 factorial. And if I simplify that a little bit, I get sigma as k goes from 0 to infinity of negative 1 to the k over x to the 4k plus 2, because I distribute squared times 2k plus 1 rather, and then all over 2k plus 1 factorial, and that now is the series for sine of x squared. Now, the interval of convergence, by the way, for sine of x was all real numbers, and so the interval of convergence of this is also going to be all real numbers. Now let's do x times sine x. Now it's important that this is just a monomial involving x. You can't have other functions and do what I'm about to do. There are ways to do it for like cosine x times sine x or e to the x times sine x, but this is not what we're learning today. It's just x times sine x. So first of all, again, I use the fact that I know that sine x is this series. So x times sine x is going to be x times this series. X times k, sigma as k goes from 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1 quantity factorial. Now remember, a series is just an infinite sum. So essentially I have to distribute this x into every single term in the series. Well, this represents all the terms, so I basically have to multiply x times this term generically with the k's left in. So this becomes sigma as k goes from 0 to infinity. I'm going to put the x with its own kind with the other x's. So the negative 1 to the k will stay the way it is. 2k plus 1 factorial in the denominator will stay where it is. And I'm going to get x times the x of 2k plus 1 turns into x to the 2k plus 2. And that ends up being the series for x times sine x. It's right there. Again, I just distributed this x into every single term in that series. So finally, we are now going to know why cosine theta plus I sine theta is equal to e to the I theta. We're going to do it by using Maclaurin series. Now we're going to have to make the assumption that these three Maclaurin series converge for all x in the complex numbers, not just the real numbers. So we start with LHS equals cosine theta plus I sine theta. So the series for cosine theta is going to be this one. I used n this time for my index. The sum as n goes from 0 to infinity of negative 1 to the n, theta to 2n over 2n quantity factorial, plus, and then I have I times this series, negative 1 to the n, theta to 2n plus 1 over 2n plus 1 quantity factorial. Now what we want to notice here is that all of the even powers of theta are real here, and they start with the first term there is positive because n equals 0, you get negative 1 to the 0. So theta to the 0 is positive, and then theta squared term is negative, and theta to the fourth term is positive, and theta to the sixth term is negative, etc. And then all of the odd powered terms, theta to the 2n plus 1, are imaginary because they are involving I. And again, the first one, when n equals 0, so theta to the 1, is positive, and then theta cubed term is negative, and the theta to the fifth term is positive, etc., etc., etc. So I'm now going to look at e to the I theta. So the RHS, which is e to the I theta, is equal to, well, this is the e to the x Maclaurin series with I theta plugged in. So the sum as n goes from 0 to infinity of I theta raised to the n over n factorial. So what I've done is I've written out a number of those terms. I've gone to the 9th term, the 8th degree term for this series, and now I'm going to simplify them a little bit. So the first term, anything to the 0 is 1, 0 factorial is 1, so it's just 1. I theta to the 1 over 1 factorial is just I times theta. Now I squared is negative 1, so I get negative theta squared over 2 factorial. I cubed, remember, is negative I, so it's negative I times theta cubed over 3 factorial. I to the fourth is positive 1, so theta to the fourth over 4 factorial with a positive 1 coefficient. I to the fifth is I again, so I times theta to the 5 over 5 factorial. I to the sixth is negative 1, so theta to the 6 over 6 factorial with a negative sign. I to the seventh is negative I again, so negative I theta to the 7th over 7 factorial. again, I to the 8th is 1, so theta to the 8th over 8 factorial, etc. So I've got the first, again, 9 terms here to the degree 8, where I worked out what I to the whatever exponent is going to be. Now remember, I to the 4th, I to the 8th, I to the 12th, I to the 16th, any multiple of 4 in the exponent of I is going to be positive 1. And then I squared, I to the 6th, I to the 10th, I to the 14th. Any even number that's not a multiple of 4, I to that number is going to be negative 1. And then, of course, I to the 1st, I to the 5th, I to the 9th, etc. When it's one number past the multiple of 4, those are going to be positive I. And then I cubed, I to the 7th, I to the 11th, I to the 15th. One number less than a multiple of 4, those are going to be negative I. So what I'm going to do is I'm going to rearrange these terms and group them in a way that's convenient. So what I've done is I've put all of the real terms of this series together. 1, negative theta squared over 2 factorial, positive theta to the 4th over 4 factorial, negative theta to the 6th over 6 factorial, positive theta to the 8th over 8 factorial, etc. I've put them all together. And then from the other ones, this one, this one, this one, this one, etc., I factor an I. So I times theta, and then I times theta cubed over 3 factorial, minus, don't forget, and then plus I times theta 5th over 5 factorial, and then minus I times theta 7th over 7 factorial. So I've got theta minus theta cubed over 3 factorial plus theta 5th over 5 factorial minus theta 7th over 7 factorial, etc., with an I in front of them. So if I look at this series, I notice that positive, negative, positive, negative, positive, etc. They're alternating, and the very first one is positive, so negative 1 to the n, that when n equals 0 you get a positive, and then it'll alternate, and then otherwise it's even powers, so theta to the 2n over that same number factorial, 2 to factorial, 4 factorial, 6 factorial, etc. So it's this series over here. And then I have this I factored out. Now when I look at this one, again, it's positive, negative, alternating. First term is positive, so negative 1 to the n. And then it's odd powers of theta, theta cubed, theta 5th, theta 7th, so theta to 2n plus 1 over the 2n plus 1 factorial that matches with the 2n plus 1. And so this series is this one over here, but that's exactly what we had over here with the cosine theta plus I sine theta. So there I can say is equal to LHS, and that is my proof that cosine theta plus I sine theta is equal to e to the I theta.